Great, thank you.
You're here, okay, good.
Yep. Okay, hi everybody. So the title of my talk is Democracy in the Pursuit of Randomness. And I want to start with a shout out to my collaborators, Bailey Flanagan and Paul Gueltz, who are my students at Carnegie Mellon. Anupam Gupta, who's a professor at Carnegie Mellon. Brett Hennig, who's the co-founder and director of the Sortition Foundation. And Greg Keeney, who's my student at Harvard. So the starting point for this talk is this quote from Jean-Jacques Rousseau, who had this to say about early democracy in England. This is 18th century, early 18th century. He said that the people of England deceive themselves when they fancy they are free. They are so, in fact, during the election of members of parliament, for as soon as a new one is elected, they are again in chains and are nothing. So this is a pretty dramatic quote, but I think still resonates today and captures some of our thoughts about democracy today, which is of course mainly based on elections. But of course the question is whether there's a different way to do democracy. And this is something that people in the workshop are thinking about, obviously. One answer that's been discussed is sortition, which is the idea of democracy built on lotteries instead of elections. Or in other words, the idea of choosing representatives at random. Now, for those of you who haven't heard of this before, this may sound like a pretty crazy idea, but it has a lot of historical precedent. So sortition dates back to ancient Athens, where some of the main organs of government were chosen by lot or at random. During the Renaissance in Florence and Venice, in the Kingdom of Aragon, which is part of modern day Spain, again, some of the main organs of government were selected by lot. But sortition essentially disappeared during the American and French revolutions that made democracy more or less synonymous with elections. However, in the last couple of decades, we're seeing a resurgence of sortition around the world, especially in the form of citizens' assemblies, which are randomly selected groups of citizens, usually convened by local or national governments. And these people are informed about important questions, they deliberate, and they reach decisions that inform policymakers. Now, this has been happening, as I said, on a pretty wide scale. So, for example, the Sortition Foundation, who are our partners in this work, organized 29 assemblies around the world last year alone. And they're just one of many organizations working in this space. So let me give you a couple of concrete examples of assemblies from the last couple of years. So for example, in Ireland in 2016, again, a couple of years later, they had big assemblies, national assemblies to talk about the constitution. And those have led to major constitutional changes after referenda. In France, starting in 2019, President Emmanuel Macron convened an assembly to talk about climate change. And this has been quite successful. So, there was a bill based on an estimated 40% of the recommendations of the assembly that was approved in May, 2 months ago. To give another example, in Mongolia in 2017, they had a very large National Assembly, again, to talk about the constitution. And another random example, in South Australia a couple of years ago, they had a smaller assembly to talk about nuclear waste. But again, these are just a few examples out of many, many examples, and we'll talk about some additional assemblies later on. Now, the topic of this talk is the process by which these assemblies are selected. So ideally, what we would want to do is, if we want to select K people for our assembly, which I'm referring to as a panel, I'm using these two terms interchangeably. If we want to select K people for this panel, we would just select them from the population uniformly at random. So this would be representative of the population and would also give everybody an equal chance of participating. However, this isn't practical because you can't force people to participate on the panel. So in practice, what happens is a different process. We start from the population, like in this ideal pipeline. But then we invite some subset of people from the population to participate. I'm referring to these people as letter recipients because usually the invitation is done by letters, but some organizations also use phone calls. So this is the set of people who were invited to participate, and these are chosen uniformly at random. But then some of these people opt in, decide to participate, to accept the invitation, and they form the pool of volunteers. And finally, the panel is selected at random from the pool of volunteers, somehow at random. Now, the problem is that while the set of letter recipients is representative of the population, and we want the panel to be representative of the population, the pool of volunteers is highly unrepresentative of the population because of self-selection bias. So let me illustrate this using a concrete example. This is based on data from Climate Assembly UK, which was, as the name suggests, a national climate assembly in the UK, which was sponsored by the House of Commons, and it was organized by the Sortation Foundation. So here the pool size was 1,727 volunteers. By the way, out of an estimated 60,000 people who were invited, so the opt-in rate is pretty low, and this is quite typical of sortation instances. And the panel size is 110, so they wanted 110 people on the panel. Now, what I'm showing here is 7 features that the organizers cared about in terms of representation. So these are gender, age, geography, education, ethnicity, area, urban versus rural, and position on climate change. And for each one of these features, I'm showing you the distribution of feature values in the overall population versus the pool of volunteers. So I want to point your attention specifically to education in the middle, where you can see that highly educated people in green are way overrepresented in the pool, and the people with the lowest level of education in blue are way underrepresented in the pool. Similarly, if you look at position on climate change on the right, the options here are very concerned, fairly concerned, not very concerned, or not at all concerned. And you can see that people who are not very concerned or not at all concerned in green and red have some representation in the population, but are essentially almost unrepresented in the pool, which is not surprising, right? If you're not concerned about climate change, it seems unlikely you'd want to spend probably weeks deliberating climate change. So given this picture, the question becomes, how do we select a panel that is representative of the population at random from a pool of volunteers that is highly unrepresentative of the population? So the way sortation organizations have invariably dealt with this is using some kind of greedy algorithm. For those of you who are not familiar with this lingo, this is basically the computer science lingo for an algorithm that's myopic, that makes decisions at every stage based on what looks good right now without looking into the future. So we've seen many different versions of greedy algorithms. To make this concrete, let me illustrate the greedy algorithm previously used by the Sortation Foundation using an example. So in this example, on the left, we have a pool of 20 volunteers, each of whom is defined by 2 features, either shape, either star or heart, and color, either green or blue. Now our panel size is 10, we want to select 10 people. And in addition, we have these quotas at the bottom, which is the way that sortation organizations guarantee representation of the population in practice. So what is usually done is that upper and lower quotas are imposed on every feature value separately. In this example, we'll just have lower quotas for simplicity. So this says that we need at least 4 stars, at least 4 hearts, at least 4 blue people, and at least 4 green people on our panel of 10. Now, the way the algorithm works is at every step, it computes the need of every feature value, which is the ratio between the number of volunteers we still need to recruit to meet the quota and the number of remaining volunteers in the pool with that feature value. And then the algorithm identifies the feature value with the highest need and selects uniformly at random among the remaining volunteers with that feature value. So let's run the algorithm on the example. So initially, the need for star is 4/10. We need 4 stars, and we have 10 stars in the pool. The need for heart is again 4/10. The need for blue is 4/11. We have 11 blue people in the pool, and the need for green is 4/9. So the highest need is for green, and then what we do is we select one of the green people in the pool uniformly at random. They all happen to be stars. So I'm showing this supposedly random selection on the right. The highlighted yellow person is the one who is selected at random from the green people. So now we need to update the need for green and for star. So now the need for green will be 3/8. We need 3 more. We have 8 remaining. The need for star is 3/9. At this point, the highest need is for heart with 4/10. So we select one of the hearts uniformly at random, and we update the need for heart and for blue. So now again, the highest need is for green. So we select a green person uniformly at random, and we update. The highest need is for heart. So we select a heart uniformly at random, and we update. And then green, select and update. So we select the heart and update, green, update, and heart. So at this point, after the first 8 selections, we have these 8 people who already satisfy the quotas. They already include 4 stars, 4 hearts, 4 blue, and 4 green. We still have 2 remaining seats on the panel. Because we've already satisfied the quotas, we can select the last 2 people uniformly at random. What I want you to notice is think about the blue star. And notice that in the first 8 rounds of selection, the blue star, there's only one such person in the pool of volunteers, they had no chance of being selected because we selected a green person, then heart, green heart, green heart, green heart. No chance for the blue star. And overall, the blue star has a much lower probability of being selected than anybody else, which seems unfair to this blue star. Now, you might say, well, maybe this is just an artifact of how the pool of volunteers and the quotas are set up in this example. We'll see in a few minutes this is not the case. Now, you might also say, well, this is just a toy example. Maybe this doesn't happen in the real world. So let me show you that this does happen. This is, again, the Climate Assembly UK data. And what I'm showing here is the histogram of selection probabilities of the volunteers. So every bar corresponds to selection probabilities in a certain interval, and its height corresponds to the number of volunteers who have selection probabilities in that interval. And the thing to notice is that the lowest bar, with selection probabilities very close to 0, has more than a quarter of the volunteers, around 450 out of 1,727. So again, you might say, well, maybe this is just an artifact of how things are set up in this example. But again, this is not the case. So this histogram at the bottom is what you get if you run a different algorithm that for now I'll refer to as the mystery challenger on the same example. And the thing to notice is that the probabilities are nicely bounded away from 0. Even the lowest selection probabilities are nicely bounded away from 0. So how do we get from the histogram at the top to the histogram at the bottom? So the way we do this is, instead of using a greedy algorithm, we directly optimize over distributions over panels. What do I mean? So let's go back to our toy example. And remember that before I said that there is something better I'd want to do in this example. So what I would want to do is select the first and third rows of volunteers with probability 1/2, and select the second and fourth rows of volunteers with probability 1/2. If we do this, then first of all, every volunteer is selected with probability exactly 1/2. So this equalizes the selection probabilities. And also notice that each one of these panels satisfies the quotas ex post. It has 4 stars, 4 hearts, 4 blue, 4 green. Right, so this is a great solution for this problem. Everybody gets an equal chance and everything, all of the requirements are satisfied. Now let's spice things up a bit and increase some of the quotas. So we'll increase the quota on star to 6 and the quotas on blue and green to 5 each. Now the thing to notice about these new quotas is that I have to select the blue star in order to meet the quotas. The reason is that if I don't select the blue star, the quota of 6 on star means that I have to select 6 green stars, but then I have only 4 remaining seats on my panel, and I won't be able to satisfy the quota of 5 blue people, right? Because all of the stars that I chose were green. So I have to choose the blue star, but subject to that restriction, I have quite a bit of flexibility. So what I propose is, in addition to the blue stars, selecting 5 of the 9 green stars uniformly at random and 4 of the 10 blue hearts uniformly at random. If we do that, we get a distribution over many panels, each of which is selected with very small probability. But the thing to notice is that every volunteer has a very significant probability of being selected. In fact, the lowest probability is for the blue hearts that have 40% chance of being selected, because every time we select 4 out of the 10 blue hearts uniformly at random. So this is nice, and we got the solution by just eyeballing this problem. But in general, we want something that would, for any example, give us a good, fair distribution over feasible panels. So to do that, we draw on fair division, which I imagine is an area that doesn't need much introduction in this workshop. The way the connection works is that we think of a distribution over panels of size k as dividing the overall selection probability of k between the pool members. In other words, the players or the agents are the volunteers, and the divisible resource is the selection probability, and we think of the utility of each player as their selection probability. Now, once we've made this connection, we can draw on mechanisms from fair division in order to think about fairness. And this allows me to unmask the mystery challenger from before. So this is the Lexington mechanism, which is pretty widely used in fair division and is known to have good properties in various domains. What it does in our context is it chooses the distribution over feasible panels that maximizes the minimum probability that any volunteer would be selected. Subject to that, we want to maximize the second lowest probability. Subject to that, the third lowest probability, and so on. And on the Climate Assembly UK data, it gives us the histogram that we saw before. Now, another natural option is maximizing Nash welfare, which is another well-known objective in fair division that has good properties in various domains. Intuitively, it again kind of tries to equalize probabilities as much as possible. And on the same example, it gives us the histogram at the bottom, which is a bit smoother. But an advantage that Lexington has is that it's quite intuitive. So when you talk with practitioners, this idea of maximizing the minimum, of making the poorest person as happy as possible, that's a very intuitive idea. So this is an advantage that Lexington has over Nash welfare and other fairness objectives. So focusing on this idea of maximizing the minimum, you might still be worried that I've only talked about one real-world example so far, and maybe things look different on other real-world examples. So, in particular, in terms of the performance of the greedy algorithm. So I want to put the last nail in the coffin of the greedy algorithm by showing you this figure, which is based on 11 different sortition instances from 7 different organizations that we've worked with. So there are 5 instances from the Sortition Foundation, which is based in the UK, and then 1 instance each from the Center for Climate Assemblies, which is based in Poland, Healthy Democracy from the US, Mass LDP from Canada, Nexus from Germany, Off-by-4 from the US, and New Democracy from Australia. And what you can see here is that for every instance, the yellow bar is showing the minimum selection probability under Lexington. The purple bar is showing the ideal equal selection probability of k over n, which I could get if there were no constraints, if we could just choose k people uniformly at random out of the n volunteers. So this is just for calibration. And then the blue bars are showing the minimum probability, in fact, a generous upper bound on the minimum probability under the greedy algorithm. And what you can see or not see is that in 9 out of the 11 instances, the blue bars are essentially invisible. And that's because the minimum selection probability under greedy is very close to 0. There's only one instance, mass LBP, where greedy is doing reasonably okay, but we view this instance as an outlier. So in this instance, the initial quotas were too strict. They basically excluded some people, and then the organizers significantly relaxed the quotas, leading to an instance which is pretty unusual. But overall, we view this as pretty conclusive evidence that this phenomenon of very low selection probabilities to some volunteers, when this is avoidable, happens in practice almost always. Now, another important point is the issue of computational complexity. So these solutions, both Lexington and Nash welfare and other solutions, are very hard to compute, both in theory and in practice. So we've worked quite hard to implement, to be able to compute these solutions in practice. And we've developed an algorithmic framework for doing this. I'm not going to go into the details, but the thing that is important to mention is that this has led to an implemented system called Panelot, which stands for panel selection by lot or at random. What Panelot does is it takes as input a sortition instance, so the features and the feature values, the pool of volunteers, the quotas, and the panel size. And it outputs the Lexington distribution over feasible panels. So the implementation of Panelot was complete around April last year, and the Sortition Foundation, who, as I said, worked with us on this process, immediately adopted Panelot. They've used it for more than 40 assemblies so far to select them, including a national climate assembly in Scotland that's still ongoing. But since then, a couple of other organizations have also adopted Panelot. So at this point, at least 6 organizations are using Panelot to do the selection of assemblies. A couple of weeks ago, we took the next step and put Panelot online at panelot.org. So now it's freely accessible to anybody, and we hope that this will increase uptake among practitioners. Now, what I want to do for the last part of the talk is talk about a particular example, an example of an assembly that met last year in Michigan to discuss, actually it was selected last year, it met this year, to discuss COVID-19 policy in Michigan. It was organized by one of these organizations, Off by 4, that I mentioned before. And what was special about this assembly is that Off by 4 put a lot of thought into how to make the selection process very transparent and trustworthy. So in particular, they put on this show around the selection process and recorded it. And I want to show you 1 minute from this recording where they explain how they use Panelot to make the selection process transparent. So this should have audio. Please, somebody let me know if you can't hear the audio.
So what we set out to do, and what we have done, is sent out invitations to 10,000 randomly selected households across Michigan. Once those of you who were willing and able RSVP'd to us, a volunteer team of computer scientists from Carnegie Mellon University as well as Harvard used an open source algorithm that they developed to generate a list of 1,000 possible panels. Each one of these has a different mix of 30 citizens who again reflect the makeup of Michigan with those proper proportions, women and men, young, old, etc. Now, each of these possible panels is identified now by a unique number, 000 through 999. The 3 machines that I have here with me, each will select just 1 digit of that 3-digit number. Together, that will give us a 3-digit number, and that will be the group of 30 that has been chosen to serve as the panel.
So this is, I think, a great example of how to make the randomness physical and really make it observable. I want to give you another example that I like. So this is kind of another scheme for doing the same thing. The idea here is that you have 1,024 squares representing 1,024 possible panels. And we're taking the point of view of a volunteer. So the red panels are, the red squares are showing the panels that this volunteer is a member of. And what we'll do is at every point, we'll spin this wheel of fortune on the right. And the wheel tells us which corner of the grid to focus on. So the first spin gave us southwest. So we focus on the southwest corner. Now we spin again and get the northeast corner. So we focus on the northeast corner of the remaining grid. And notice that the volunteer can keep track of how many panels they're still on, what their chances are. The next step is southeast, so we focus on that. We need 2 more spins to get an answer, southwest, and finally northeast. So we ended up with this one panel that happens to have the volunteer on it. So this is, another idea to implement the randomness physically and kind of make the process exciting and trustworthy, but you can think of many other ways of doing this using dice or whatever. But the crucial thing is that all of these methods require a distribution over panels. So you can't do this if you use the greedy algorithm. So this is another advantage of doing things this way. But it doesn't require just a distribution over panels. It requires more specifically a uniform distribution over a given number of panels. So in the examples that we saw, in the first example, it was 1,000 panels. In the second example, it was 1,024. And we specifically need the distribution to be uniform, like a uniform lottery over these fixed number of panels. Or in other words, every panel in the support would have probability, that is a multiple of 1 over t, where t is the desired number of panels. So if, for example, a panel has probability 3 over t, it would appear 3 times in this list of panels, and then we choose uniformly at random from the list. Now, you might worry that constraining the probabilities in this way would lead to a degradation in terms of unfairness objectives, like maximizing the minimum probability or Nash welfare. And it turns out that this is not the case, both in theory and in practice. So in theory, what we can show is that for any distribution over feasible panels of size k, we can construct a uniform distribution over t panels for a given t, such that each individual selection probability differs between the 2 distributions by at most k over t. And by individual selection probability, I mean the selection probabilities for the volunteers or members of the panels. Now, if you think about k over t, so remember that in almost all of the real world instances, k, the panel size, is at most 150. I only know of one exception, that assembly in Mongolia, which is larger. T, you can choose to be as high as you want. So in the examples, it was 1,000 or 1,024. You can easily make it 10,000. If you have 4 lottery balls instead of 3, T would be 10,000. So, this is easily very small in real world instances. Now notice that this also has direct implications for fairness objectives. If you think about the minimum probability, this directly implies that the minimum probability would increase by at most k over t by doing this. And you can also draw conclusions for Nash welfare, although that requires a bit more work. Now, in practice, as is usually the case, things are even better. So here I'm showing you a figure that's similar to what we saw before. The bars are showing the minimum selection probability for the 11 instances. Yellow, like before, is showing Lexington. This time, blue is showing the constrained Lexington, which is Lexington but constrained to probabilities being multiples of 1 over 1,000 for the case of 1,000 panels. And the thing to notice is that the blue bars are almost as high as the yellow bars, meaning that the loss in fairness, according to the subjective, is very, very small. The green bars are showing what happens when you plug in the parameters of each instance into our worst case guarantees. We actually have a couple of different theorems, so this is showing what you get from the best one. The thing to notice is that even these worst case guarantees give nice bars that are nicely bounded away from 0 for 9 out of the 11 instances. So this says that the worst case guarantees are meaningful in practice, but of course the actual performance is better than the worst case guarantees. So the takeaway message from this is that the loss in fairness is very small due to enforcing these uniform lotteries and being able to really make things transparent. Oh, sorry, I opened the wrong presentation. This is the full version of the talk. So I'm going to just skip to the take-home message, which is, so the take-home message is going to look a bit cheesy for this audience, but let me say it anyway and then discuss it a bit. So the take-home message is that computer science and math have a role to play in improving the practice of democracy and potentially in shaping its future. And like I said, I think this is somewhat obvious for most attendees in this workshop. But what's interesting in this, from my viewpoint, is that a few years ago, when I talked about social choice, for example, in courses, I would often say that it's very difficult to impact the practice of democracy because of tradition or because of political considerations. And there are various examples where it was difficult to change voting rules, for example, even though it was very clear that alternative voting rules were much better. But what I've learned from this experience is that it's not impossible to actually make some impact on the practice of democracy using these mathematical and computational tools. And to me, this is very exciting. Okay, so just finish with references. So the talk is based on 2 papers. And again, because this is the Rodin version of the talk, we'll see 3 references, but really the first 2 are the relevant ones. So the first is work with Bailey Flanagan, Paul Gueltz, Anupam Gupta, and Brett Henning. The paper is called Fair Algorithms for Selecting Citizens' Assemblies. It's in Press and Nature and is scheduled to be published on August 4th. So if you want to see the official version of the paper, you'll have to wait a few weeks. If you want a horribly formatted informal version, please feel free to write to me and I'd be happy to share it with you. And the transparency part was based on work with Bailey Flanagan and Greg Keeney. The paper is called Fair Sortation Made Transparent. We finished it in May and it's currently under submission. And the third reference, like I said, is a paper I did not talk about in this talk. That's it. Thanks so much. And I'm happy to take questions.
Thank you very much, Ariel. Right. So questions? Ariel?
Thanks, Ariel. Two questions. First, a little one, a bit technical, but I did not understand when you mentioned your theorem about restricting the number of panels to T and the approximation that doesn't lose more than K over T. What was the motivation of that? Since the exercises is to do a computational tool, why would people be interested in, instead of having 1,000 panels to have 300? I mean, is there a practical reason for that?
Yeah, so this is motivated. This is motivated by the kind of examples of making things transparent. Where if you have 3 lottery balls, then you want you want 1,000 panels in that example with each with an ID number, and you want the lottery balls to indicate the ID of the panel that you select. So this means that you need a uniform distribution over exactly 1,000 panels in order to be able to implement it with 3 lottery balls, each with digits from 0 to 9. So that was the motivation for that restriction.
Okay. Now a second question, a bit more general in a sense. Suppose the goal is not fairness, but actually, distorted fairness. I mean, I know in the population parameters A and B, C are represented in such proportions, and I want in my panel to have different proportions. Is that something you can easily adapt the algorithm?
Yes. So essentially what you're saying is, I mean, one way, I can think of several ways to address this. I think one way would be just to impose quotas that are different from the proportion in the population. Right, so you can still have a fairness objective like Lexington, but implement your distorted representation using the quotas. You can also implement it in the objective, and our algorithmic framework is pretty flexible, but probably the easiest way to do it would be through the quotas.
And if it's computable, you could do Nash with power coefficients and things like that, you think? Or maybe that would be a bit weird? I don't know. I mean,
Nash, yeah. So what do you mean Nash with power coefficients? Coefficients on the probabilities?
Yeah. I mean, I don't know. I mean,
yeah. So you need the objective to be convex. I mean, basically the restriction on high levels, you need the objective to be convex in the individual selection probabilities. Subject to that, things are pretty flexible.
Mm-hmm. Okay. Thank you.
Other questions? I have a question, or rather an observation. So actually, when you showed the first slide with the statistics, yeah, it looked for me very optimistic that the people who are actually most interested in the issue self-select into solving the issue, or probably more competent in solving the issue self-select into solving the issue. So it looks like the procedure is self-adjusting. Even if everything is random, just one step that is non-random, this voluntary participation, self-adjusts. And then while you were presenting your results, I like them very much as just a local optimum, or optimizing, solving the local problem. I couldn't help but actually was critical regarding the solution of the global problem. I think when you give politicians this tool that they can use the way they want, so adding more categories or deleting some categories, this tool that you give them should be at least paired with some additional research onto that says who is most competent in solving the problem, which composition of this panels are best, or who is most concerned about the problem because they will be affected most, and so on. So just congratulating us that mathematicians finally can influence the politicians directly. Well, I think it is a bit too ambitious. So we should still be careful providing them with these tools.
Yeah. So
yeah, that's what I want to say.
I think it's an interesting comment. I mean, if I understand correctly, I think the concern you're expressing is relevant in democracy in general, where when we have elections, some people are better informed, some people are completely uninformed and choose for the wrong reasons. So this is something that's kind of inherent in any democratic system. And political theorists do view this idea of equality of opportunity as one of the ideals of democracy. So if you're kind of explicitly taking into account competence level, which is something that has been done in history, like in Belgium in the 19th century, they would give more votes to, if you were wealthy and if you were educated, you would get higher weight in elections. So this is something that basically died out, because today we essentially believe that even if some people are less competent, and of course these are also very weird proxies for competence, but even if some people are less competent, we believe that everybody should get an equal opportunity. So I think you're making a good point, but these ideals are kind of in tension, and it might make sense to kind of think more about how one might resolve this tension.
Thank you. Would be happy to continue during the dinner, but maybe next year, hopefully, or the year after. Thank you very much. So we have our next speaker.